Yeah, thanks for the invitation. I'm enjoying learning stuff about level inference. My talk is kind of preaching to the choir, looking for information beyond the Gaussian regime in weak lensing. But I want to focus a little more on the two systematics that actually follows very nicely Natalie's talk, because I want to focus a lot on how you take care of baryons and intrinsic alignments, and how you calibrate these beyond the 2-point regime. These were basically everything I've done is done by everything I'm talking about is done by two students at Columbia, Max Lee and Brian Liu. These are my more senior collaborators. If I say anything, I should just compulsory. I'm here for less than 3 months officially in Austria after 25 years in the US in Columbia. And I'm at ISTA, just in case you don't know, we are here. ISTA is located here. It started 15 years ago, and it looks like this. All the buildings are new, except for the administration building, which used to be a mental institution. And has been converted to the admin building. So the philosophical questions addressed in my talk are, first, just in idealized world, how much information is there in a perfect weak lensing map? And then going to the practicalities in the real data set, how much we can go beyond the 2-point functions and systematic effects. We all know that the universe mass distribution is not Gaussian. It looks like that. Weak lensing is a projection of this along the line of sight, which makes it much more Gaussian than this, but it's still not completely Gaussian. These are maps of kappa, the weak lensing convergence, integrated essentially with a ray tracing code to this filamentary structure. And these are identical, these are maps where one is a real large-scale structure, the other is generated on a Gaussian random field in 2 dimensions with the same exact power spectrum. I think actually somebody made such a point in a 3D matter distribution. This is in 2D lensing. You can see by eye. Actually, I sometimes make people vote, but I know only 15 minutes, so I just give away the answer. You can see by eye that the Gaussian field is different from the lensing kappa. There are many more bright hotspots in the actual universe than in the Gaussian random field. And so that's actually can be converted one of the statistics. But in terms of how you extract this information beyond the Gaussian regime, of course, there is the whole point of this conference of field level inference. Traditionally, you can do perturbative expansions, endpoint functions, or high order moments. And we heard great talks about this. You can go and define other morphological features on your maps, peaks, Minkowski functionals, minima, shapelets, etc. You can, another approach I haven't heard, but I wasn't here in all the talks, is to Gaussianize this field, apply some transformation and convert it to something that's more Gaussian, that buys you something. And then the approach I'm going to just mention in our group we followed is machine learning, in particular, generate maps and train a neural network in simulation world, and then ask the neural network to guess the cosmological parameters. There's been a lot of work on this over the last 10 years or so in the context of lensing, so I'm not going to describe how deep convolutional neural network works. I just want to say one point about it is that you basically do n-body simulations with Gadget, you do ray tracing, you generate, let's say, 1,000 realizations of these kind of maps in, let's say, 100 different cosmologies, and then you train the network. And then you do, the way we do inference is you ask the network to predict the input omega and sigma 8, but then you treat these outputs as just 2 numbers, x and y, or y1 and y2, and then you can proceed the same way as normally with the power spectrum. Say that you have a likelihood because you know the distribution of y1 and y2 for a fixed input omega matter and sigma 8. You can obtain a likelihood and posteriors and get constraints on your parameters in a mock observation. If you do this, again, this has been known for 7-8 years now, that if you just do an inference like this in omega matter sigma 8 space, the red is what you would get from the power spectrum. one thing I used to be very excited about, I still am, is counting peaks because it's so simple. You make a bin histogram of peaks on the map. Even I can understand how that looks like. Number of peaks with a particular height, function of peak height. If you use that as your statistic, you get the green. And then this neural network got us the blue. And technically, it's 13 times smaller area than the power spectrum. And I think I had the same reaction to this as Thomas when he mentioned the result. We scratched our heads for a few months whether we made some mistake, but it looks like this is actually real. For example, if you do this analysis on Gaussian maps, the contour from the machine learning is the same as the power spectrum. It learns the power spectrum. It doesn't overfit something. So I think all this, and this is idealized, going to arc-minute scale on the map. So this is just nothing but just a proof that the answer to this first question is basically a lot, at least an order of magnitude more information is there on small scales if you can access it. Can we access this information is the next question. So before I go to the systematics, I just want to say that I have the student, Brian Liu, who 2 years ago did a very heroic exercise, bravely training the networks on the simulation suite that we generated, and then applying it to the HSC Year 1 catalogs. So these are very nice. We are not involved in HSC. It's public information. You have a catalog of shear for 8.5 million galaxies. In this redshift range, each galaxy has a position, redshift, shear, and the weight. And then also has PSF residual errors, photometric redshift errors. And you can forward model this entire data set. So we generate 80 cosmologies, and we add baryons. I'll explain in a second how, with 4 additional parameters, which means changing the profiles of the halos in the n-body simulation to accommodate effect of astrophysics. So we generate a few million maps this way, and then we train a network. And again, every galaxy in the simulation is located at the same redshift, same sky position, has the same weight as in the real data. Then we add shape noise, basically by randomly rotating the observed galaxies. We add the baryon effects with 4 parameters, moving the mass, changing the profiles of the dark matter halos. We add 1 parameter for intrinsic alignment, which I discuss in a second. We also had shape measurement error and marginalized over PSF residual errors. You do all of this, then you get an output. Again, I don't want to focus, I just want to say that this analysis was quite, I was quite happy or pleasantly surprised. We didn't get a result that omega matter is minus 13.5 and sigma 8 is 10. We actually got reasonable numbers. This is the corner plot. And blue again is peak counts, green is power spectrum, and red is the neural network. This is omega matter, this is capital sigma 8, and these are the baryonic parameters. So the main conclusions here are that baryons actually blow up the errors by quite a bit, factor of few, but and the neural networks improve the error on omega matter. And without the baryons, they would also improve the error on sigma 8, but with the baryons, sigma 8 is not constrained much better by the neural network. And then the baryon parameters, you can see here, they're basically not really well, they're basically not constrained. So the extra info from the neural network is a factor of 3 improvement on omega matter. And again, mostly by taking degeneracy and not improving along this best constrained direction. 2 other interesting results are that the sigma 8 tension in this analysis basically goes away, because the best fit model in this analysis is one where the baryons suppress the power and then sigma 8 is increased to compensate. And so you actually get closer to Planck sigma 8. So formally by 2.2 sigma, you go to 0.4 sigma. And then the baryons affect omega matter only modestly, but sigma 8 by factor of 2 degradation. And that's the result. We still gained quite a bit by this neural network. Again, this is a partial result because we didn't let all the cosmological parameters free, but I think we did a good job on trying to forward model this data set. Now, I have 7 more minutes, then I would. Okay, let me just say, so I can shorten things, but the 2 main systematics that we're grappling with here are the baryons, which change the mass distribution, and then the intrinsic alignment, which are correlated, not random. And one way to proceed with the baryon is that you use hydro simulations. Then you have a parametric model, which describes how, compared to an n-body, the gas physics changes the profile, and this is parameterized by 4 parameters. The issue that we are trying to address here is exactly what Natalie raised previously, that these models are calibrated on simulations, but using the power spectrum. We wanted to check how they will do on the non-Gaussian statistics, if you take the same models. Clearly, that's required. If you believe the simulation, you should also reproduce some non-Gaussian statistics. Second is, if you believe these simulations, then in principle, these simulations also produce galaxies, and those have alignments. So you could actually ask in these simulations, if I measure and take into account intrinsic alignments, how do they affect the shear maps and the statistics? These are the 2 things for which I have a few minutes. The first one, I should just say, we therefore took Illustris. Again, this is a public data set. It's great for this kind of analysis for outsiders because it is public. It has about 1 million well-resolved galaxies in this mass range. And the great thing is that it has a dark matter only version, and then there's a version with hydro with full star formation and AGN physics. Good resolution, 300 megaparsec volume, and they have halo and galaxy catalog. You can do this kind of thing. What you have to do, of course, is do the whole analysis of ray tracing and produce shear maps, which is what we did. I think most people probably know what these baryon correction models do. I already described, they change the profiles. For me, the greatest achievement is that you don't have to actually wed yourself to Illustris or any simulation. For example, this is the power spectrum, and these are 7 different hydro simulations, only one of which is Illustris in the red. The others are different hydro simulations, and the curves are demonstrating that if you tune the parameters of this baryon model, you can reproduce all of these simulations. So that's a way to say, if you believe these simulations in general, but you don't know which is correct, you can accommodate it. But this is the power spectrum. So we did the simple exercise of calculating my favorite statistic, which is the number of peaks. Again, the procedure is, as I described, you take Illustris, you modify the halos in the dark matter simulation to mimic baryons. Then you ray trace to produce shear maps, and then you plot histograms of the peak counts. And you can compare the dark matter simulation with the hydro simulation, and then the baryon corrected dark matter simulation. There are 3 curves here. The most important result is here. These are peak counts. The 4 panels are different depths. This is 10 galaxies per square minute, like DES or KIDS. The deepest is Roman, 50 galaxies per square minute. This is the fractional difference in the peak counts. The solid line is the difference between the baryon-corrected dark matter and the hydro. And you can see that here it's within the big errors, and here it's outside the errors. So with LSST Euclid-Roman, you basically cannot just take the BCM model that's calibrated on the spectrum and use it to describe non-Gaussian features. But up till now, you could do that according to this. Looks like I have only 1 minute. 0. Okay, you can actually, I can say the rest in words. The same Illustris simulation, you can also study intrinsic alignment. And if you believe the Illustris hydro and how it affects the gas profiles, maybe you should also say, I should also believe how they form stars. And just to make a point that they're actually real-looking galaxies, you can do mock observations. So what Max, another amazing graduate student at Columbia, did was to go to this Illustris simulation and basically pretend that this is the data. And you fit an ellipticity to each of the Illustris galaxies. and pretend that you're measuring the shear. And you go through this whole process, and you predict, you make shear maps, and you predict peak counts. Some other non-Gaussian statistic. Then you can compare this with another analysis where you randomly rotate in 3 dimensions all the illustrious galaxies. So you erase the effect of intrinsic alignment. So this comparison is what here. I just go to bottom line, which maybe plot. Again, this is the difference in the statistics. This PDF peaks, number of minima, and this curve are the relative difference between this analysis, including the intrinsic alignment and randomizing and taking out as if there was no intrinsic alignment. And this difference basically is, again, outside the errors. So this just shows that if you build a simulation, then the intrinsic alignment produces an effect which will clearly bias your results. That's all we can conclude so far from this. We can also say how. Basically, it looks like the very positive and very negative kappa pixels get enhanced by the intrinsic alignment. There are clear next steps here. You should compare this to the NLA model that people normally use and see how that works. Up here, these are the conclusions. I won't read them again. I think one philosophical note I should end on is, what is the meaning of believing these simulations? Because I think it's very useful to analyze and compare how baryons look like and how intrinsic alignment looks like. But you have to decide what you do with this. Do you really believe one simulation, or does everybody who does a hydro have to repeat this whole analysis and then you have to compare? It could be a big discussion.
Thank you, Zoltan.